In search of soil.
So, David, I mean, the first thing I really wanted to ask you was in all your years of dealing with microbes, what has been the most fascinating thing to you? Is there one thing that really stands out, just blew your mind when you found it out?
Well, gosh, there's a lot of things, but I think what really started to put it together was the influence of our own stomach, our microbiome in our stomach on our health and our well-being, and the number of things that they do and their relationship to our health, how they're about 80% of our immune system, and their ability to turn on and off genes in our body. All of this is fascinating, and it just transferred to the soil. You know, how we're seeing a regeneration of that soil microbiome has so much influence on the productivity of the system, nitrogen fixation, phosphorus solubilization, and as we bring it back, how much influence it can have. I mean, that has to be the biggest eye opener. You know, we woke up one morning and we had to pinch each other to make sure this wasn't a dream, that it was real. The potential that we saw to bringing these microbiomes back in soils.
Where do you think agriculture's current understanding is of microbiology when it comes to soil? I think we can say we know it's there. We know it's more complex than we'll understand. But do you think agriculture really respects how important it is and how important the balance of those microbes are?
At this point, there's very few. The people that are out on the leading edge are seeing this. They know that's it. But we're still probably back in the 60s looking at microbes as pathogens exclusively, not as beneficial parts of the system. But we're getting there. I mean, we see Monsanto and Bayer start to bring out biologicals now because they see this is the future. It's just a matter of time. I think this will be the agriculture of the future. Our understanding is still very limited on this. We're just scratching the surface, and it's such a complex system, elegantly complex, but complex nonetheless as far as the decisions we make in agriculture, how we treat the soil, all the different operations that we perform on the soil. We still have a lot to learn on that, but there's so much potential when it is brought back properly. You know, it's what we're seeing both in rangeland and cropland.
If we look at rangeland or cropland, where do you think the biggest miss is right now in terms of biology in those soils? So we're not talking chemicals or anything like that can obviously harm that biology, but in terms of the biology present in those soils, are farmers not doing enough to encourage the right kind? Are they not doing enough to encourage any kind? Are there just too much of one? Where do you see soils right now in
Well, I
agriculture?
think most of the practices that we've adopted over the last 150 years have been degrading soil microbiomes, either through plowing or disking or the application of all the different biocides. All of this has been a negative influence on building soil biology. And as I was saying, those farmers and ranchers that are out on the leading edge, they understand that that is what they're raising, is the soil biology. The bacteria are the grass of that system as far as the consumption by organisms at higher trophic levels. And they're understanding that if they do the right management techniques, they can bring those soils back. You know, and many of them have. You know, we've seen some very interesting changes in rangeland. South of us here in the Chihuahuan Desert, we have one rancher that's gone from 250 acres per cow to 25 acres per cow, just with grazing management. And this is not an unusual story. You know, we see another rancher here in central New Mexico, Nancy Ranny, how she's gone from 4 species of grasses to 45 species of grasses in less than a decade, and bringing back what, you know, in our area. I live in the desert, and it's the desert because of one reason. It's because we overgrazed it. It used to be grasslands belly high to a horse when the Spaniards came through. But then with our grazing techniques, we grazed it into a desert. And nice to know is with proper grazing, you can bring it back. But that seems to be the only mechanism and as you know, what developed on the Great Plains with the bison and how they were kept in tight herds with predators and they were moved along at regular intervals. They deposit their dung and their urine and their saliva, basically inoculating that grazing land every time they would go over it, because the manure would be rolled up into small balls by the dung beetles, placed in the ground and composted in place. It was just a great inoculation event, and it built up some impressive grasslands. I mean, soil carbon 5-6 feet deep, the ability to grow forage in even low water environments. I mean, the rancher Alejandro Carrillo, south of us, he gets 7 inches of rain, and yet he's brought it back from a complete desert, just scrub, mesquite, and greasewood, and he now has grasses belly high to a horse. So we can do the same thing in our cropland as well, focusing on restoring that microbiology in the system. And it's a system. That's what we need to look at it as. It's not just bringing back fungi. It's not just bringing back bacteria. It's a whole system that we have to recreate in that cycling of the carbon and cycling of the nitrogen. It's an energy equation. We have completely destroyed the productivity of these soils. We're working with compromised photosynthetic capacity on these soils. And as we bring this biology back, we can increase the amount of photosynthesis, the capacity of that certain area of land to actually capture the sun and capture the carbon and restore that system. The biology seems to be key. It is for us, and it appears to be the same for the soils.
When you go from 4 species to, I think you said 40 species in that example, what's changing in the soil to allow those extra X number of species to now say, I can grow there? It's not just all manure being deposited. In other words, if we just took grassland and we just put manure over the top of it or compost over the top.
No, it's the restoration of that system. It takes a certain amount of disturbance as well. I could recommend a video that Peter Bick put out on a rancher in Texas. That the name of it is Herd Impact. You can get it on carboncowboys.org. He has 10 short mini documentaries on how these rangeland or these grazers have changed their soil. And this particular one in Texas, in order to restore the soils that were just barren, it took a certain amount of impact on that soil from the hoof action. It's, as I say, it's a system that we're trying to bring back in all these different components, even to the design of the hoof of the cow and how its impact on the soil, the saliva and also the tearing of that grass when the cow eats it produces hormones that increase plant growth, as long as you don't take it back too far. In the Great Plains, usually only about 40% of that forage was actually consumed by the animal. The other 60% was either trampled into the ground or left there for a food resource for microbes. So there's a certain amount of the carbon that has to go back into this system in order to start rebuilding these soils. But if you have reduced photosynthetic capacity on the front end, which is what we're really fighting right now, unless we bring that back, we're not going to be able to build the carbon up in the soils the way we should be able to. And the fungi we're finding on a research project, again with Peter Bick in the Southeast, looking at about 5 pairs of ranchers doing either the adaptive multi-paddock grazing and a conventional for at least a decade. What I'm seeing in the research that I've done is it's the fungal community that we've destroyed in all these systems. It's the most fragile, but the fungi function as both logistics and communication. They transport elemental nutrients that in cooperation with the bacteria in the soil to the plant in exchange for the energy that that plant is captured to fund or energize that system in the soil for the microbes to be able to extract or fix the nutrients from the atmosphere. And if we can't bring back that photosynthetic capacity, we're not going to really be able to fix these soils. But the nice thing is we can. We've seen in this research the ability to increase productivity 5 times on forage production in these systems as you bring this biology back. It starts stacking on itself, increased carbon into the system. We're also seeing on the back end a reduced respiration rate, at least a relative respiration rate. The carbon that stays in the soil longer, you get a better carbon use efficiency. Most of the ranchers or most of the scientists are going to look at this and see, okay, you've increased carbon by 14 times. You've increased the soil microbial community biomass by 5 times. According to the current perspective, you're going to increase respiration. But the funny thing is, as you bring this fungal community back, as you bring the whole system back into operation, you are going to respire a little more carbon, but it levels off. So relative to the amount of carbon that you have in the soil to start with, that could be oxidizable or respirable by the microbes, they don't respire it. They put it more into biological growth than into respiration. And that increasing the biology in the system increases the ability of that system to extract the nutrients from the soil parent material. And the system just starts stacking and building on each other. More nutrients available, more energy and carbon available in the system, more plant growth. At least that's what I'm observing. It's not only in grazing, but in cropland as well.
You talk photosynthetic capacity and increasing that to build up the below ground biology. What is it above surface that's happening that's helping below surface? Is it just more sugars coming out of the roots, more exudates coming out of the roots? So the more you can grow up top, the more is being pumped out below?
I think a lot of it is that, having the microbes there to make the nutrients available for, in photosynthesis and in nitrogen fixation, they're all protein structures that are performing all these metabolic functions. And in every protein, you have metal cofactors that allow these energy conversions to occur. Photosynthesis depends on magnesium, as far as the capture of the energy from the sun. But there's a whole suite of other proteins along the line in the transferring that energy that are required for an efficient flow of energy. If you don't have the microbes in the soil to extract those nutrients and make them available, I'm talking more than just nitrogen, phosphorus, and potassium. These plants use almost all of the 92 naturally occurring elements on the periodic table. There's no way as farmers and ranchers that we can contemplate what we need to add to the system or what we need to make available as far as these micronutrients to make the system function properly. And yet nature has, over the last 45 million or 53 million years on grazing land, has developed a system that's quite efficient at doing this if we allow it.
If we look at the Great Plains as they used to be, and I know there's, I think, some still small sections of like the original still intact with these deep, deep soils. And then we have cropland that has been treated conventionally for, let's say, 100 years. And it's what we'd classify as poor soil compared to that Great Plains soil. Can you walk kind of through a step-by-step process, not in terms of how, but in terms of as we change our management practices, what would happen to that poor soil on its way to becoming that deep Great Plains soil? What does that story look like?
Well, yeah, I have to take you back to what we're seeing in the human microbiome. In one instance where they've done an experiment and they've removed fiber from the diet of mice to see what happens to their stomach microbiome, they have a decrease in diversity in that system. the more generations it goes through, you just get a decreased diversity all the way through. You would think, okay, we'll bring the fiber back, just bring the carbon back in your soil, but it doesn't restore that microbiome structure. It doesn't bring back diversity. The only way it brings it back is if you come in with an inoculation from a healthy microbiome. And we're seeing the same thing in humans, that if people suffer Crohn's disease, IBS, decades, some people die from it. Some people have resections of their intestines, more antibiotic regimes. And yet they find out that if you can bring the microbiome from a healthy individual, like in a fecal transplant, and put it in to the person with IBS or Crohn's, in many cases, they can be cured in 24 hours. And it seems to be that essential or important in these soils that we've broken, is to bring that biology back. We see it just with an inoculation of the compost in the bioreactor. We did research in a project in Wilcox, Arizona, where we came in with 2 pounds of compost per acre as an extract that we injected into the furrow at planting. In that research, what we saw is we compared a conventional approach with 256 pounds of nitrogen. We had an intermediate treatment with 15% of that, or 38 pounds of nitrogen in that 2 pounds of the compost. And then we had another treatment just with the compost, the 2 pounds per acre rate. What we saw is we matched productivity to the conventional with the beam or the compost plus 15% productivity, 15% nitrogen, that 218 bushels of corn. And this was quite unexpected because we replaced probably 180 pounds of nitrogen in that system just with biology. And in the compost only, we only suffered a 6.6% loss in productivity. So there was, again, about 140 to 150 pounds of nitrogen that we brought into that system just with the biology. So it's, from what we're seeing in this research, is that you need to be able to bring a healthy community back into this. And the compost process that my wife and I developed seems to give you a very robust and diverse microbial community. We see, as you allow it to mature, we see a 4 times increase in the diversity of the microbes. You'll see microbes that start out in the composting process, and at the end of that year, they're not dominant. Some of them aren't even present, but they've been replaced by a whole nother suite of microorganisms that have much more diversity and much more capability. So again, we're learning a lot on this. It's not all known. We're still at the very beginning, and say scratching the surface, as I was saying earlier to you.
Is inoculation enough? Meaning, well, I mean, in the sense of there has to be food in that soil for the organisms you're putting into that soil to consume. So, and I know this is generalizing, but do you think that most soils, there's enough food there for microbes? If you add microbes, at least some will be able to proliferate, multiply, and establish themselves? Or do you need that inoculant plus food source for the inoculant at the same time?
It's, again, a system. And the microbes won't do it by themselves. This is not magic. They need a living plant at all times to have that carbon flow. It's kind of like banking. You need a certain amount of money going into your savings account in order to build things up. But it's a system that we're trying to restore, and having a plant grow all the time, either a cover crop or a commodity crop, is essential to restoring the biology. It won't happen without plants. It's that relationship that developed between the soil microbiome and the plants that make this planet what it is today.
So I know from watching some videos of presentations you've done, when you've applied some of the compost to different properties, it's very sparse, I would say, compared to what some people do. Imagine you took a sheet of white paper and you kind of threw a handful of seeds on it, you're going to see a lot of white around those seeds. And that's the rate that you're applying, and you're seeing a big difference. I know, at least in the small scale farming world, a lot of compost application is you have a white sheet of paper, you put compost on, you have covered that white sheet of paper and you can see zero white. So on one hand, your hand, you have the concentrated inoculant going into the soil. On the other hand, you have people just piling compost on. Do you think that an approach of just constantly putting on compost is it's working, but maybe you're working too hard, or it's not really a means to an end? And is there some way that people can move from this, just dump it on, to a more sparse application?
That's what we're seeing. I started out at 400 pounds per acre, which is a dusting. So it's not a nutrient amendment the way we're developing this. It's an inoculant of the microbiome. We're down now to 2 pounds per acre, right? So, and having success. I mean, the farmer was $80 an acre more profitable by using the compost from this bioreactor and that research in Wilcox. So, and this was on a very, very poor soil that we started. It was very compacted. I mean, some of the infiltration rates on it were above 10 minutes. So it was a very compacted soil. The cover crop, we did grow a cover crop on it before we planted this first year. And instead of growing into the soil, the root mass would push the soil up. So when you drove over it, it was like driving over a corrugated surface. So we didn't start with a great soil on this. And we did have one cover crop under our belt on it. But then we came in with the biology, and we saw that dramatic improvement in the productivity without the use of nitrogen amendments. So it's a system that we're bringing back, and understanding that it's not magic. It's just biology, microbiology, and it depends on a constant flow of energy, just like we do. If we don't have energy, we're cavemen. If we have a little more energy into the system, we start to be able to do more things. We start to be able to procreate more. You start even more energy. You start to have specializations of the different organisms. A little more energy into the system. Eventually, you'll have synergy in these systems as you bring the biology back and the energy into the system. It's all about energy flow on this planet. And it's the microbes that developed all the different protein structures to capture that energy and to channel it through in living organisms. And this is what we have to try to restore, is that whole system that evolved on the planet, and to our benefit as far as being able to grow the food that we need to grow.
You're restoring a poor soil is more better initially, and I'm thinking small scale here. Somebody who has 1,000 acres, they love the sound of 2 pounds per acre. Somebody who has 1 acre could say, I could do 2,000 pounds on my 1 acre. That's not a problem for me to distribute that out. Is there an assumption, or is there a direct correlation between you took really high quality compost that is a food source and an inoculant in one, and you put more of it on a poor soil initially, you're going to get results that much faster?
Yeah, I can just relate what I've done in the research. I just did an experiment looking at the influence of garden, and these are still low rates, at 2 pounds, 5 pounds, 10 pounds, and 20 pounds per acre rate. I saw no difference in the productivity between the many different rates. But what I did notice I had another experiment going on beside it of a in-furrow treatment. All those were in furrow. They were sprayed in as I planted the seed, but I had one where I sprayed the inoculant on top of the surface. And then I watered it in immediately. There was double the productivity of the injected into the furrow at planting compared to spraying it on top. So it was pretty dramatic to see, these plants doing double the productivity, same amount of water, same amount of sunlight, and yet the productivity was so much higher when the biology was right there with the seed when it germinated. So higher rates, I don't have the data in between 400 pounds and 40 pounds. That would be something to look at. But as I've been looking at larger scale productivity, because I know we need to make a change. I see so many farmers hitting a brick wall as far as they've destroyed the soil fertility. They're making cents an acre on profitability. And yet they know they can't pass this land on to their son or their daughter because it would be a burden to them. And yet, as you bring back the system and its functionality, farming becomes fun again. I've never seen happier farmers and more profitable farmers. And those that are starting to look at this as a biological system, that are starting to use that power of observation to say, okay, what do I need to do next? It's not always, it's not intuitive. Nature depends on diversity. Diversity not only in the community of microbes are there, but also in the activity that goes on above the soil. As far as what you plant, when you plant, how do you treat this? How do you treat that? There's a full lifetime of education in farming. It's not all easy button. You do it this way every year. So there's a lot to learn, but observation will be key.
It sounds like that's a case where, an inch could make a big difference. I'm thinking, you're drilling in seed. It's not going in that deep, but you're injecting the inoculant in with the seed as you're drilling it in versus you put it on soil and then you water it in. It just intuitively to me, it doesn't seem like number two, the water in method would leave it that far away. But apparently there is enough of a difference there that biology needs that root interaction right away to really get going. Like, why do you think that is?
Yeah, it's just having that community available as it germinates. And, the Haggertys in Australia, when they do a very similar injection rate. It's 2 kilograms per hectare, which is almost identical to 2 pounds per acre. And you can see pictures of the seed and how much just barely germed. The cotyledon's only about an inch long, and yet the rhizosphere that's developed in that community that is impressive. It's devoted a lot of energy to associating with those microbes, and if they're not there and available, it just seems like the plant just flounders. I could show you a picture of what it looks like. There's a dramatic difference of where I've injected and where I sprayed it on top.
So on a small scale for somebody farming, maybe the ideal way to get this going would be if you're doing a lot of transplanting of your plants, would be when you're seeding these plants, you're either coating that seed or you're quote inoculating that seed in the beginning in the nursery. So when it goes into the field, you're transporting that cube of soil that has not just roots, but a community with it that goes into the soil, and then it can multiply out in the soil once it's there because the plant and obviously that community are staying together.
And seed coatings work. The Haggertys also, they spray their seed with the inoculant but as they feed it into their hopper. I've done some experiments where I've sprayed the seed and planted it dry and sprayed the seed and planted it wet. And there's a dramatic difference between dry and wet. Wet will outgrow the dry treated quite handily. So it's having that living community available at germination that seems to make this work so well.
For at this point in the episode, we're talking a lot about inoculant compost, your specific way of making compost. So I want to introduce people to the idea of the type of compost you make. At its core, what are the base principles around the compost that you're using?
The method that we developed maintains 4 key factors on this. It's aerobic. It always has oxygen. The way the bioreactor is designed with the columns up the middle, you're never more than 6 to 12 inches from ambient air. So it's a completely aerobic process. It's a process that operates at about 70% moisture content. That's critical. It's undisturbed. You never turn it. You don't need to. As long as it's aerobic, as long as you have the 70% moisture content, the biodegradation process goes forward, and it seems to increase in diversity, the microbial diversity, the longer that you let it go. Also, we employ worms in it. So it is a vermicompost as well. And the worms, we only put in about 100 worms, the red wigglers, at just after it gets down past 80 degrees Fahrenheit, so you don't cook them. And they will, about 100 of those will populate that pile completely by the time it's done, and it'll be full of baby worms. And the ending texture is a lot like clay. You know, you can squeeze it between your fingers. You can squish it into a ball when it's done. And the microbial community is pretty impressive. When I do metagenomics on it, we see about 2,700 species of bacteria. We see probably 400 to 500 species of fungi. So that's another thing, that's having it 70% moisture content, having it aerobic, that allows fungi to proliferate. And you end up with a significant number of fungal spores, because over that year, you start to consume all the energy resources in that compost. So what does a fungi do when it runs out of food in its environment? It'll sporulate, so it can live when conditions are better. So we see a significant number of spores. And that's what we're putting in with the extract, is we're seeing spores of fungi and also a lot of bacteria. So it's restoring that community through that process.
With a clay-like texture at the end of it, I think that's different than a lot of compost you see people buy that looks more like, say, kind of mulchy. It still has identifiable bits of organic matter in it. It would have a different hand feel, more loose, kind of friable. What are the big differences you see in Johnson Su bioreactor compost versus traditional compost? If you just drive to the landscape yard near you and they sell compost, what are the differences in those methods in the end
Well,
product?
the methodology, they're turning that compost several times in the first week. So the fungal community never really gets to develop. And every time they turn it, the system reheats up. So you don't go through that phase. In this composting method that we use, you're through the thermophilic phase or that heating phase within a week, and the temperature starts to go down. And it depends on what you put into it. As far as how high the temperature goes, the more nitrogen you put in there, the higher the temperature will go and the longer it will stay. But normally, the heating phase is 4 to 5 days. After that first week, you're pretty much through, and the temperature will start going down. And this whole system allows that fungal community to dominate. So you don't see that in turned compost, because every time they turn it, they destroy all the fungal hyphae. I mean, you can see this within 24 hours after you fill that bioreactor. In the method that we use, you can go and you can start to pull the organic matter that you put in apart, and you can see all these hyphae, both of the fungi and the actinomycetes, just completely populated the pile. So, you know, the pipes that we put in the middle, I think there's 6 pipes that we put in there. After 24 hours, you can pull those out. I mean, the hyphae from the actinomycetes and the fungi have completely threaded that pile together. So you have a column once you pull those pipe out that doesn't collapse. Now, as it matures, the whole system will start to fold in on itself. You'll end up with something that looks like a very rich, dark chocolate cake at the end. And if you grab it and have any moisture in it, you can squeeze it, and it does just meld together like clay. You know, that's what we're observing in the compost process.
I think one of the biggest comments I've seen on the one that I built was a lot of people have suggested add this to it, add that to it. They're all nitrogen sources, and they're all saying do this and it'll speed it up. And they're missing the point here that the goal isn't fast results. The goal is the right results, and that just takes time. So if you did try to speed this up by adding fish emulsion or whatever to it, What are you trading off? What are you missing?
That's a good question. Um, I tried at the beginning on some other, before we developed this, by trying to add nitrogen to the system to speed it up. It failed. And what I see is, a lot of the resources I use to make these piles are very low in nitrogen. I mean, you're talking leaves, 50 to 60 to 1 or higher. And I saw that the benefit is allowing the system to fix its own nitrogen with free living nitrogen fixing bacteria. You start to develop those community of microbes that can do that. And I saw there's plenty of nitrogen in the composting process because I see a lot of free living nitrogen fixers. That community develops very strongly in these composts. I've got the metagenomic data that I can show you. Well, this group right here, they're free living, and they're a major component of the system. So I think the more you can leave it alone and let nature take its course, it's like a good wine or a good cheese or good bread. All of these, it's a system that you kind of let nature do what she's done for millions of years. And the results seem to show a much better compost.
So is this idea that you see a lot out there of 18 days to finish compost, 30 days to finish compost, do you think that's doing more harm than good, where you're adding organic matter to the soil and that will help your soil in the long term, but it's like you're only focusing on half the picture, you're not seeing the whole picture?
I think from the research I've seen, if you can allow nature to do it in her time frame, the results are much better. I mean, I don't know that they can use theirs at a 2-pound rate and see this type of benefit. I know the Haggertys observed in Australia, they got their compost from one person on the east coast of Australia, and they're on the west coast. They had it shipped all the way across Australia, which is not a small country. And they thought, well, we'll just use somebody else's compost. And it failed. So I think, that's what we're doing an experiment right now to see how consistent these composts made all across the USA, to see how different they are or how similar they are. So that will hopefully answer a few of those questions that we have on it. As I say, there's still a lot we don't know, but what we do know is it's beneficial to plant growth. It can be applied for a cost from 25 to 50 cents an acre if you're a large farmer. It grows great tomatoes just straight. If you're a regular farmer just doing a garden at home, you can't go wrong with this stuff. It really makes a difference in the way plants grow.
What are your thoughts on forcing air into the system, injecting air into the system, where you're not turning it? You take that exact same setup, you observe all the other base principles, and you're not keeping it moist, only you are blowing air into it. I've read some studies on that, and it seems like fungi can just increase their efficiency, growth rates with more oxygen present. I see, okay, well, you are using an outside input. It requires some extra parts, but I don't see it changing what you're going for that much. What are your thoughts on that?
Yeah, from what I would think, you would dry the pile up if you're forcing air through it. This is we developed this basically both for third world and to be able to do it in a first world country with parallel processing. The bioreactor is 4-foot diameter, 5-foot high. We wanted it as energy free as far as having input. The biggest input is 1.5 gallons of water a day being sprayed over the top and allowed to go through by gravity to keep the moisture content at 70%. So that's the only energy impact into this system. I think we were concerned, I guess, more with third world when we designed this, just to make sure that they could do something like this. And we do have those bioreactors going in 3 different countries in Africa, India, Pakistan, Siberia, believe it or not, Crimea, all over Europe, New Zealand, Australia, South America, Central America, and many here in the US and Canada. So I think it's the less energy input, the less work you have to do with this, the better off it is. I don't think you'll speed it up that much by blowing air, because as long as the pile's aerobic, what more does it need? It doesn't need any more airflow as long. And the research I did, I found that anything more than a foot into a compost pile goes anaerobic within minutes. So we're never more, as I say, more than 6 inches to a foot away from ambient air. So this pile stays aerobic all the time. So I can't see the need to actually pump air into it.
Okay. No, fair enough. And another big question I see is, kind of answered it there, but give me your thoughts on this. Is I'm doing this here in Southern California, nice weather year round. A lot of people in temperate climates have said, well, how does this work in an area where I have 4 months of true winter? You mentioned Siberia. If you go from a warmer climate, or say a tropical climate, to something, temperate and cold, do you see performance, or you just need more time?
If you can keep it warm, keep it from freezing. We've had one large one done in central Colorado, where they had to put it into a greenhouse, and they used a different system, same principles, but they did a 30 by 40 foot bioreactor with all the pipes and everything, and a floor underneath that allowed the airflow, and they were successful. They produced a really good compost, about 100 tons of it, and the pile did get down to 32 degrees, but when they went in and dug, the worms were still active. So it may take a little more time in a colder climate, but you need to keep it from freezing. It's a living organism. The worms in there are transiting and having their impact on the biodegradation process and all the other organisms as well. So if you can either keep it inside, we had one dairy farmer in was it Manitoba that keeps it in his dairy barn, and his cows keep it warm. And we had another one in Quebec that is looking at, he keeps an anaerobic pile going that he can maintain airflow to keep the temperature of that pile up. He has a water loop through that, and he runs that into an aquaculture that he keeps good to minus 45. So it's, you can stack hay bales around it, maybe put a heat tape underneath it. Just innovate as far as trying to keep it from freezing. Put it next to a warm building and hay bale that, or inside. Some people are doing it inside in their shops and just keeping it, where it won't freeze. But there are tougher environments. Yeah, we're in New Mexico, so that's not an issue. Although we've been down to minus 16 for 3 days in a row on some of my bioreactors, and not above zero, and they still did fine. So as long as there's a warm up period after it.
Yeah, and the great thing about it, you want to put it inside a barn or shop, is I haven't noticed any smell. I know you claim that. I can verify that. There's no odors. There's no flies. None of that. You're not watering enough to have like water drain through the bottom of it. So it's a relatively, quote, clean system to have inside.
Yeah, it's quite unique that it doesn't smell. And that's the biggest problem. What shuts down composting operations is the smells, the odors, and also the effluent that runs off from the process. But there's no runoff from this process when it's done right, and there's no smells as long as you put the pile together right. You won't have smells.
Does the system scale up and down if you keep those same base principles? Never more than 12 inches away from oxygen. So if we had enough up pipes that we eventually removed, we kept it at that moisture content, could I go bigger? You had a 30 by 41, so obviously you can go a lot bigger. Could you go smaller? One thing I've tried a lot here over the years before I even discovered yours is I've done this in trash cans, where I drill holes in the side of a trash can down the center. I've always put a tube in there. After I saw your system initially, I didn't, but just put the tube in the center.
It took me a little while to figure it out.
And it works really well, I think, on home
scale. It took me a little while to figure it out too. If it wasn't for my wife weighs 10, this bioreactor would never be. Okay, I would have been turning compost by hand in a windrow.
Sure. So credit to her, because it makes it easy. And I always left the tube in there, and then I went back and watched the videos, and he's pulling the tubes out, and I was really nervous to pull the tube out.
Yeah.
And
I was too.
No problem.
Yeah,
Yeah.
the school of hard knocks and serendipity here.
Right.
and
Right.
and the wife saying, "I'm tired of washing your clothes. We're going to do this different."
Yeah. So just do
Yeah.
it. Do it. So yeah, I mean, with the system, can you scale up and down? Is there, or do you need a critical
I
mass?
We have some people scaling down. You know, I can never have enough of this. You know, you put about 2,000 pounds of wet material into it in this size bioreactor, and you end up with 700 pounds product. So, you know, if you're a farmer, you can get what, 350 acres. Looks like if it's a really good compost, you could probably get a full section off of one bioreactor. So, you know, how much do you need? Uh, as I say, you can never have enough. For, at least when you're doing research and people asking you for it, all that. But you know, one bioreactor can cover a lot of area if you need it to, and yet you can parallel process them. You know, make more units, start them at different times, have them available at different times. You know, it's really easy to with the finished product just open that cage up and be able to access the compost the way we designed it. You know, and then you can close it back and hold it, just keep it going. The finished compost, if you have any left over, we'll make a smaller bioreactor, you know, about a 2-foot diameter, about 18-inch high, and we'll put the compost in there. We'll throw, you know, a drip system or irrigation system on it to keep it wet, and we'll put alfalfa on the top to keep the worms fed. But it can go for a long time. I've had some up to 4 years, and eventually I had to use it. So I don't know past 4 years, but it stayed good up to 4 years. As long as you put some alfalfa, ground up alfalfa on top to keep the worms fed, and they're doing what they do in the system.
One of the more popular trends in smaller scale homesteading gardening for vegetables is wood chip mulching over garden beds. If you think about the base principles behind the bioreactor, we're never more than 12 inches away from oxygen. We're keeping it moist. It's slow. What are your thoughts about, let's say we didn't put the material into the bioreactor and we just laid it down on our production beds? It was only 10 inches thick, so even the bottom wasn't 12 inches away from ambient air. We're watering it to keep it moist. Do you think you're losing anything in that type of system versus having it in that cylindrical bioreactor? So composting, quote, in situ versus creating compost in a composting
You
device?
know, since you said wood chips, the wood chips, I only use wood chips in this at the beginning because I started with dairy manure. I'm now just using straight leaves or straight alfalfa to compost, just something that breaks down easier. The wood chips are ideal for the garden. I think any type of cover that you can offer to that soil to allow that in situ restoration of that microbial community, I do it on my garden. I mulch my garden heavy because, well, number one, I can't keep up with the weeds if I don't do it. And it's so much more beneficial as far as I use less water, you know, and just to have the biology working there, you know, I don't have to haul it in. So I definitely recommend mulching for if you have a garden. It's just a no-brainer when it comes just to the weed issues. You know, they keep a nice environment there where you have your roly-polies, and they will pretty much clear cut anything that tries to sprout underneath that mulch. I found that out the hard way with a cover crop that I rolled and planted cotton into. Uh, the roly-polies would come in and clear cut my cotton. So, you know, you do have to do transplants that way, unless you protect a seedling, a seed, you know, either with, I'll use a quart glass jar for when I'm seeding my cantaloupe or my tomatoes or my chilies. I'll just put a jar over it till it germinates, and that keeps, you know, the insects from coming in and clear cutting it. So you know, there's a lot you'll learn on this as you go through the process. Again, observation is really helpful.
Well, one thing I love the idea of is multiplying it out in the form of an extract. So let's say you did one bioreactor, 2,000 pounds in, 700 pounds of finished product out. Now you want to increase that and essentially turn it into more than 700 pounds. How can somebody go about making the extract to coat seeds with?
Well, on the seed coating, if it's strictly a seed coating, I would go with a slurry. That's really simple. Take about 10 pounds of compost, and I'll add a cup of milk that has about a tablespoon of molasses in it. And then I'll add enough water to make a slurry, like a pancake batter. I'll push that through a screen to get all, any of the large organic matter that didn't degrade, something that would go through a seeder, small enough. And I will take 1/4 of that with a 50-pound bag of seed, and I'll tumble that in a cement mixer for about a minute and a half to coat the seed. And then plant it as quickly as you can, even damp. It will still flow. It'll actually flow better, a little damp in your planter if it's a large system. And then you've got that slurry coated seed. The extract is different. You just make an extract. I have a YouTube channel that most of this is available on, as far as making the slurry and coating the seed or making the extract. So that's another mechanism. If you forget what I say here, you can go on YouTube and just look for me, and then you'll find my channel. And there's not great videos, but I think enough to help you get the idea of how it works.
Yeah, I mean that's what I use actually to build mine, so I found it very
Oh,
helpful
okay.
for that. Yeah. Along the lines of extract, what are your thoughts about using it as a tea?
Okay.
Put some in, bubble it, and then use it as a foliar spray, not to provide nutrients to the plant, but just to get that beneficial microbiology on the surface leaves of.
Okay. Yeah, the Haggertys do that as well. They'll do a seed coat, an injection, and they come back with a foliar after the plant's about 6 to 8 inches high, and they see benefits. Now, when I look at making a tea, as you're saying, you're brewing it, you're putting in food resources to boost the microbial community. I've done some analysis on the community of these systems, and as you brew it, you start to bias the population. You start to lose the diversity, where the microbes that can utilize the nutrients that you put in there will increase in population. The others that don't, that are maybe secondary or third down the line on the different byproducts of other organisms, they will fade away. So I saw a loss in the diversity of the system as you brew it, just because of the nutrients that you add to the system.
Do you think you could maintain that diversity yet get the benefit by doing something like this? I add some number 5 cups of it to a bucket. I fill that 5-gallon bucket with water. I just stir it around enough to agitate it and kind of cleanse the material, organic matter of anything that's on the surface. And I've mixed it up. Now I use that straight. So I just stir it and go right onto the plant.
That's basically an extract. I just recirculate. I have a system with an agricultural pump, and I recirculate it to a 55-gallon drum. And I keep washing the compost with that water that's recycling. So that's, the extractors online as well, but you're right, it's just knocking the microbes off the organic matter. And what we're seeing, I did some analysis on this, we were seeing about 83 million bacteria per square foot put into the field, in that field in Wilcox, and a little over 10 million fungal spores at that 2-pound rate. So per square foot, that's a pretty significant number of microbes, especially when you bring that diversity back in.
You seen any correlation in any of your studies between the amount of, quote, weeds in the soil and the progression of that soil from something that's more bacterial dominant to something that's closer to in balance, fungal to bacterial?
Only what I've heard from Australia, where they saw about year 8 into the system, they start to exhaust that weed seed bank. Having the cover on the soil rolling those covers is very helpful in keeping weeds down. We saw that in Wilcox. And we have an aerial of that. And we were looking at where they've applied the conventional synthetic fertilizers. The weed pressure was much heavier in that treatment than it was in either the beam with the 15% or the beam only. And beam is biologically enhanced agricultural management. It's just using, restoring biology into the system. But we noticed from an aerial significant weed pressure from the use of the synthetic fertilizers. Now, you kind of shoot yourself in the foot, because as you apply the fertilizers, it makes a soil more amenable to weed growing in it. The weeds they serve a purpose. They're there trying to restore that soil. And you can watch the different sequences as you improve the soil, that you'll move from one weed to another. Like here in the desert, if you go out and scarify the soil, you'll have tumbleweeds for 3 years. And after that, another weed will come in to help restore that soil. But those seeds are out in the desert. And yet, that desert, if it's undisturbed, they don't germinate. And yet, when you come in and disturb that system, you see that the tumbleweeds will germinate, and they're voracious in growing. I mean, it's amazing what a tumbleweed can do in a shorter time. But it's as you keep the covers on the soil, you have a complete community of microarthropods in there eating those weed seeds up. That's another thing. The different parts of this system, the microarthropods and their function, the beneficial insects and their function in the system, as you bring all these back into this system, it starts to function properly. We've come in and we've cut it off here or cut it off there, create a problem. So this is where the observation comes in. Like we were talking to some cotton farmers in Turkey, and they were having a red mite problem. Well, they're also having thrips. Well, there's thrips that feed on the red mite population and the eggs that the red mites lay. So you have to start developing that beneficial insect community as well in this system. It's an elegant system. It's really neat to study and see how things work when they work properly. But we need to allow that to move forward and to promote that as much as we can in our agriculture.
A lot of people listening to this are growing annual vegetables in a system where have a crop go in, then you're rotating it out, the next crop goes in. Is this crop rotation, if you're pretty in terms of your timing, where one crop comes out, next crop goes in, is that enough, quote, permanent cover? Or do you think you could go even further for vegetable farmers, like having a perennial cover crop growing in addition to the vegetables? Or is the rotation of vegetables sequentially enough to get the above ground part working to feed all that below ground microbiology?
Well, we see Singing Frog Farms in California. They do 6, 7 different successive crops on their land. And they're seeing that they come in with sets, but they'll cut the other previous vegetable off at the surface, leave the root in the soil, and just plant the next vegetable crop into that soil. And they're being very successful at it, and it's enough to pump them out of carbon into the soil for those organisms to survive, it looks like. They were having to apply compost before, but I think they've moved away from that, and they've completely restored that system and that community, where now it's pretty much self-supporting as far as the carbon flow, the energy flow, as long as you have something growing.
What have you seen with your research with Beam of just that? Do you think you can get to the point where you can get off compost, or if not, can you get down to that 2 pounds per acre level? Can you get the system where it just grows itself and you are never making compost again to improve it? You might make compost because you have the organic matter around and you need to do something with it.
Oh, I think if you're just using it for commodity crops, you'll have to inject every time. Now, when I put it down at 400 pounds per acre and I kept a crop growing, I never had to add again. And I kept seeing year after year after year of successive increase in growth. We saw a 5 times increase after the first year, and we saw another 5 times increase from that year to year 6. So if you put it on heavy and keep it covered, keep something growing, I don't think you'd ever have to apply again. But if you're using it in a commodity crop where you have row cropping and you're putting it in at such low amounts, I think you would have to keep doing that until you could build your soils up, and that would involve, having covers in between or bringing grazing in. But if you're putting it that light, I think you would have to do it every time. That's research that we want to do, but it hasn't. We haven't got the funding to do that yet. We're working on some other projects right now.
Do you have any thoughts on soil mineralization of, let's say, annual crops where you're exporting biomass from one property somewhere else? And if you're not reapplying some sort of biomass to reintroduce minerals, are you exporting minerals from your soil enough to detrimentally harm the soil? Or do you think that there's enough minerals in the soil, the more biologically active the soil is, it can mine it from the bedrock, all of the little bits of rock and things like that in the soil? So this idea of remineralization maybe isn't as important as some people might emphasize?
As long as you have the biology and as long as those elements are there in that soil parent material, they can be extracted by the microbes. That's how this planet developed. We take such small amounts out, 96% of it that we pull off of a field is either carbon, hydrogen, oxygen, or nitrogen. All of those have been gases at one time, and you're pulling them in as a gas. They're in the atmosphere. They're freely available. The other elements, you are pulling some out, but it's such a small amount. And, like phosphorus, we have probably over 40 years supply of phosphorus that we've dumped in the soils that's inaccessible to a plant because there's not the right biology there to make it available. Due to soil physical chemistry, the phosphorus gets locked up and the plant can't access it unless it has the right microbe. And we saw 15 species of phosphorus solubilizers in this compost, or we developed in soils where we had applied the compost. So pretty much, if the element is there, it can be extracted by the microbes. We even see that one microbe can extract gold from soils. And if it can do gold, possibly the most impervious to breakdown metal, if they can do gold, they can do pretty much anything. Now I qualify that as long as you have the nutrients there. In some cases, like the soil we're working with on one research project, they don't have selenium and they don't have molybdenum. Molybdenum is very important in nitrogen fixation. It's a cofactor in the enzyme for fixing nitrogen. We also see selenium is very important for immune systems in plants, in how they react to other organisms trying to attack them, and even viruses. So if it's there, I believe that the microbes could mine it. If it's not there, you may have to supplement. And I usually will do a total elemental analysis on the soils that I start to work with, just to see if there's any underlying issues of one element missing. So critical, like molybdenum. I mean, if you don't have that, that will hamstring your ability to fix nitrogen. That's key in this system, is having those organisms function properly.
When nitrogen's fixed, it's expensive in terms of carbon. Maybe it's like 10 to 1. I forget the exact ratio.
12 to 1. 12 units of carbon for 1 unit of nitrogen.
Does that give some credence to this idea of growing a nitrogen fixing plant with another type of plant? If you think of this Three Sisters example, beans grown with corn, with squash, beans are fixing nitrogen. The nitrogen fixation process requires a lot of carbon to make that happen. Maybe the bean can't produce enough itself, so now you have another plant, corn and or squash, which is pumping out its own source of carbon into the soil around those beans. With, does it make sense to have a nitrogen fixer and a non-nitrogen fixer paired together to make sure there's enough carbon in the soil, or is the biology just going to do that?
I, I think I've always gone with mixed species, multi-species covers, just to try to take advantage of that synergy that develops between plants. There's really interesting research done in Canada, and they compared multi-species covers to a single species triticale. And you can see in they didn't get a lot of rain, and the triticale didn't get but calf high. And yet in the multi-species mix, same amount of water, when the fields were right next to each other, you had a cover crop that was above your knees. So how these plants work in synergy together is another great thing that we need to explore. You know, they help each other in many ways in the flow of that energy. So, and the utilization of water.
You're seeing a increase in above ground biomass with the beam approach. Does quality of product move linearly with that? So sometimes, a big blueberry looks good, but it doesn't necessarily taste as good as a smaller blueberry. Do you see plants growing big and expressing their genetic potential how they should? Or are they growing big at the expense of, say, whatever commercial goals we might have for that plant?
Yeah, it's so there's no comparison on tomatoes. We did 62 pounds of tomatoes on one tomato plant in this stuff, just playing around. And the taste, of course, commercial tomatoes have no taste. We're starting to look into the nutrient availability, and the tests are very expensive. So it's something that we're working towards now. We have some things going, but that it would be the next step. If you're growing more biomass, does it have more nutrients in it? Is it more nutrient dense? And that's a great question. I can't answer that one yet. All I know is that we have much higher sugar content in these plants. And I know that the cows, when they see these plants, they will make a beeline towards them as compared to, your regular pastures. But cows are pretty smart, very selective. They'll test all the different available plants in a field before they'll go graze. So they know.
Higher sugar means more efficient rate of photosynthesis and or more photosynthesis?
Yes, it's directly correlated to photosynthetic capacity, because you're making sugars. Everything on this planet is made from sugar. That's the original building block for everything on this planet, every protein, every fat. It's interesting that it all comes from sugar.
So if you have an above ground portion of a plant that is struggling, what's happening below ground that's potentially causing that? Let's assume it's not under insect attack. There's no herbicide or anything like that. Let's just say it's poor biology. At the root soil interface, what are some things that might happen below ground that would negatively affect what's happening above ground?
Oh, just not having a complete community there to do what needs to be done, kind of like a factory. If you're manufacturing cars and a few of your workers don't show up, it stops the whole process. It's having all the organisms there to function in what job they do. And nature won't always pick the same, because a lot of these organisms have multiple capabilities. A lot of your Pseudomonas, they have several capabilities in carbon cycling and nitrogen cycling, phytohormone production. There's just having the community there that can do the job, very essentially. If there's no other issue, if there's nothing wrong with the chemical or the elemental component of the soils, If it's just the biology, then it's probably just not having the right microbes there.
Because I think a lot of people miss this. I think they think the root goes down and it just sucks up whatever it needs out of the soil, but it needs something in the soil to present to the root, and then there's an exchange there. So is that what's probably potentially missing?
Yeah, and our own perception of us, we don't realize that we're cell count, we're 90% microbial as a human. And gene count, we're less than 1/10% human. It's predominantly microbes is what makes us up and what makes us operate. Well, it's the same thing for the plant. The plant, I think the plant is our artificial experiment one for microbes, artificial intelligence. And it wasn't mobile enough, so it tried us. We're number two and kind of went awry somewhere on us.
If you think humans, a lot of people in studies have now shown that there's a direct link between health and the amount of gut flora that you have and the diversity of gut flora. Have you seen enough in terms of observation and data to say that plants grown in the healthier soils in your trials are more resistant to pest pressure and
No,
or
yeah,
disease?
yeah. And other people, their research that they've done. The higher bricks, actually, insects don't like a higher bricks plant or a higher sugar content sap. They will avoid. Usually, insects are attacking the stressed plants, those that are having trouble. And but yeah, there's research that I've seen that pretty much demonstrates, the healthier the soil is, the healthier your plant is, the less impact that you'll have from insects.
Same thing with fungal diseases, blight, and things like that in tomatoes, where maybe they're very susceptible at a certain time of year in the poor soil, but this could increase their
What
resilience.
I noticed when I was first starting doing this, we were in a greenhouse with another researcher that was studying soil fungal Phytophthora on Chile. And we noticed that an extract of this did as well as any of the fungicides that they were offering on the market. So what you're doing is you're bringing back what I see as a competitive innovation. You're bringing back a healthy community that can repel any particular organism being dominant, like Phytophthora. We've heard of them also. If you'll dip seed potatoes in this, or you dip a tree that you're going to transplant, you get a better transplant, or you get a reduction in the attack by different fungi in the system. So it's like us. We depend on that diversity in our microbiome for our health, and the soils are the same way for the health of that plant. It depends on that diversity. And it's, as I say, it's competitive innovation. Everybody keeps each other in check. Instead of having a niche that gets destroyed, like you put an insecticide in there and it kills a certain niche of microbes and causes a problem, because other organisms will move into that niche. If it be they pathogens, then you've got a problem. But if you have a whole community of interacting microbes that keep each other in check but beneficially work together, then it's a system that seems more amenable to profit in farming, at least.
What are your thoughts on the importance of mycorrhizal fungi and putting those into a system when you plant seeds in? They require living roots to survive, so you can't multiply those out or create them in a compost pile. Do you think using them in parallel with type of compost in your system or another high quality compost makes sense? Is it beneficial, or is it kind of like just you might see results, you might not?
You know, the spores of mycorrhizal fungi they're floating in the air, they're in the soils. What I noticed is you bring a balanced, diverse microbial community back to the system. I saw 23 species of mycorrhizae develop in a soil. So I think it's more having the environment, having all of the players there that can really bring the mycorrhizal community up. You could try a test area and see if it helps. I always recommend that to farmers. Try it, small test area, and see if you get any benefits from it. For the most part, I think they're there. They just don't have the right environment to survive in. They need the helper microbes. Just like all of us depend on somebody else in this society for production of a good or to buy what we do. So it's the same thing in the soil. It's a biological barter, so to speak, and having all the organisms there, some of them can start to thrive that couldn't before. That would be your mycorrhiza.
Try it in a small area, see if it works. Are there any ways for people to kind of see where their soils are at now? If say they think they have good results now, and they think, oh, like my vegetables are growing great. I have great tomatoes. I have great lettuce in the field. And they're wondering, okay, could it be better? Is the best thing to do, you got to try it? Or is there some sort of test? Can you see this under a microscope? Can you send a sample of soils somewhere to say, okay, what does my community look
like? From what I've observed as a molecular biologist, I don't see a good test yet. I see a lot of, looking at fungal to bacterial ratio through microscopy. You can get such a varied results that you can't really make heads or tails of what's going on. I mean, if it's blatantly obvious, yeah. But I've sent compost samples, the same compost sample in, and had it analyzed 3 times, and I got 3 different results going from bacterial dominant to fungal dominant. So that scares me away from, it is helpful. Phospholipid fatty acid analysis, the originators of that test to look at the microbial makeup of that system, say do not use it for a fungal to bacterial ratio. So you can use it for change over time, but not as a good comparison because they depend on phospholipid fatty acids, and that we've put certain groups of phospholipid fatty acids into one group, saying they're fungal based, and some bacterial based. But there's bacteria that produce the fungal phospholipid fatty acids, and there's fungi that produce the bacterial. So it's not a great test for doing fungal to bacterial ratio. I think the science is still weak in that area. I know my wife puts it this way, that there's not one single test that lets us know if we're healthy as a human being. We have to go through a series of analyses in order to really, maybe even then, figure out what's wrong with us. I think we know more about humans than we do about soils, so we're way far behind as far as being able to diagnose the health of a soil.
You think it's worth the average person, farmer, to get a microscope
Oh,
and
yeah.
look at their...
Yes. Just the realization, looking at the life in that soil, realizing it's a living organism. That kind of puts the perspective into that, well, maybe I need to treat this different. Seeing that much life and that much activity going on, excuse me, in the soil, it's eye-opening for a lot of people to see all that activity.
Another thing that I think a lot of people maybe judge their soil quality on, if you send it in for a soil test, the number that comes back is there's an organic matter percentage on there, and a lot of people hang their hat on. I have.
Oh, yeah.
Is that potentially misleading? A second part of that would be, is there a percentage of organic matter that's too much? So if you have too much organic matter, biology isn't consuming it fast enough. And that might say, okay, well, there's a bad problem. You're just dumping organic matter onto something that just can't eat it quick enough. What are your thoughts around percentage of organic matter in relation to soil health? And is there an upper limit where there could just be too much?
Yeah, it's not that simple. But what I've seen as far as soil carbon, now a lot of farmers, just anecdotal evidence, seeing how their soils and how their plants respond. They're seeing a change at 3% soil organic carbon, or soil organic matter, excuse me. That'd be about 1.72% soil carbon. They see the dynamics change in how a plant grows. And I did a greenhouse experiment looking at, change in soil carbon and a change from bacterial dominant to fungal dominant. And I saw the maximum productivity, the maximum photosynthetic capacity occur at 3% soil organic matter. Same place that farmers saw it. So I think there's some truth to you do need a certain threshold of carbon in that system for it to function properly. It's an energy vehicle. It's an energy resource. It's it's the biology as well. But I don't know that too much. We see Gabe Brown hitting 8-10%. Up to 12% in some of his soils. I've not seen a problem. He had 5 inches of rain each year for the last 3 years on his pastures. And yet we went to visit him in July and he had grasses up over the hood of his 4x with 5 inches of rain. Now he's completely changed the dynamics of that soil, brought the carbon back, brought the soil biology back. And to have a system that efficient that it can use 5 inches and produce that much forage out on a pasture is amazing. Most people struggle with getting forage grown, but with his grazing management that he uses and how he treats the land, he has some impressive results.
For as good as his soil is, do you think his soil could benefit from some of the extracts that you talk
No,
about, or applying this fungally
I'm
dominated
trying
compost
to I'm
at
trying to
that
catch
point?
up with Gabe.
Yeah.
Since he has the grazing, that you don't need this if you have grazing. I'm just trying to emulate what nature did and what he's doing, what Will Harris is doing, Alejandro Carrillo. All of them can outperform me with the animals. But we can do pretty well. We can definitely restore and regenerate these soils in agriculture with this system.
So where it might be useful in a grazing context is if you are, some of the earlier examples you had, you're starting with a poor pasture or a limited species pasture, and you're trying to move that along quicker. In addition to your rotational grazing, you could introduce some of this compost to help get that inoculate going, get the flywheel moving in the system. But once it's going,
Yeah. As I said, the cattle, the grazing makes everything go forward. It will help, maybe. We're starting to look at some inoculations and grazing management, but the jury's still out on it as to what the impact is.
putting this all together for people watching along with this at home, I think the big takeaways for me are one, slow down on your composting. Maybe change your process to get a more diverse compost that maybe errs on the fungally dominated side. Because I'm gathering a lot of soils are probably maybe more bacterial dominated to begin
Oh,
with,
yeah, we're
but more
very
fungal.
bacterial dominated is the problem. We don't have the
Okay.
fungi.
Which is, I think, a big misnomer. I think a lot of people have this assumption that tree crops need fungi and herbaceous plants need a bacterial dominated soil. And maybe that's true for some herbaceous plants, but not the ones we typically grow.
Normally, from what Lane Ingram has shown, it's about a 1-to-1 fungal to bacterial ratio, and we're sitting in ours at 0.03. So we are very bacterial dominated in our agricultural soils here. I mean, it's practically no fungi in the system.
So get some fungi back into the system, restore that biology, and then keep some sort of living cover on surface to keep bringing nutrients and exudates and sugars down into that system, and then just kind of watch it go.
Step back,
Yeah,
resist.
yeah,
Don't try to do anything. Try to
right.
just observe, and maybe you can help it, but most often, if you just observe, you'll figure out what you need to do next.
If you found that that's a curse, and maybe you have that too, of we want to try and do too much, the human wants to try and move it along. I mean, you pick up any agricultural catalog, and the amount of soil amendments and things you can pour onto your soil is insane. Where yes, we need to maybe steward or kickstart this along to undo a lot of what we started, but it really is just at some point, it's just time and good stewardship.
It's hard to resist trying to do something.
Great. Hey, you want to build a bioreactor, a Johnson Sioux bioreactor? They can look up your video, find plans of that online. Where can people go to learn more about the work that you're doing and
Yeah,
follow
I
along?
suggest California State University, Chico. They have a Center for Regenerative Ag and Resilient Systems, and they have a lot of good speakers on there, a lot of good videos. All the process for building this. There's a lot of people that have registered on that site. I definitely suggest the Center for Regenerative Ag and Resilient Systems at Chico, California.
Perfect. Well, thanks for taking the time to chat today, David. I
Well,
really
thank you
appreciate
as
it.
well. I wish everybody the best on this. I hope it works for them. Happy composting.
Hi, everybody. Thanks for watching. Subscribe here to get the latest from the show. Also, be sure to check out some of the great clips and watch the full interviews right here on In Search of